Good morning, everyone. Today we are going to see natural convection heat transfer. It is a fascinating process driven by temperature-induced density differences without external forces like fans or pumps. Natural convection is key in applications ranging from home heating to atmospheric circulations. Unlike forced convection, which relies on mechanical devices, natural convection occurs spontaneously when a fluid is heated or cooled, creating fluid motion that transfer heats. In this lecture, we will explore the mechanism behind natural convection, Newton's law of cooling, and critical dimensionless numbers like Rashob's and Rayleigh. We will also convert heat transfer over vertical and horizontal surface in enclosures and real-world application. By the end, you will understand how natural convection works and its role in engineering and nature. This process is vital for designing passive cooling systems, optimizing thermal insulations, and understanding environmental phenomena. Let's get started and see how density-driven fluid motion shapes heat transfer around us.
Let's begin with the fundamentals of natural convections. Natural convection occurs when temperature variations in a fluid causes density differences, leading to fluid motion without external forces like fans or pumps. For example, when air near a hot radiator warms up, it becomes less dense and rises up, drawing cooler air in to replace it. This process is passive, relying solely on the fluid response to temperature changes. Natural convection is common in heating, cooling, and ventilation systems, such as radiators in home or passive coolings in the buildings. It is prevalent in natural phenomena like ocean currents driven by temperature gradients. The heat transfer rate depends on the factors like the temperature differences, fluid properties, and surface geometry. In engineering, natural convection is valued for its simplicity and energy efficiency, as it requires no mechanical input. Understanding this process helps to design systems that leverage natural fluid motion for effective thermal management. So let's explore the mechanism behind natural convection in the next slide. Mechanism of natural convection is driven by density or by the buoyancy, which is caused by temperature-induced density changes. When a fluid is heated, it expands, becoming less dense. For example, air near a hot surface warms up, reduces in density, and rises due to buoyancy. As it rises, cooler, denser air or fluid moves downwards to take its place, creating a continuous circulation. This fluid motion transfers heat from the hot surface to the surrounding fluid or vice versa. Imagine a warm radiator. Heated air rises, cools at its releasing heat, and sinks, forms a convection loop. This process is self-sustaining as long as temperature difference exists. The strength of the circulation depends on the temperature gradient, fluid properties like viscosity, and the geometry of surface. In engineering, this mechanism is harnessed in systems like solar heaters or passive ventilations, where natural fluid motion provides efficient heat transfers without energy-intensive devices. Understanding this cycle is key to predicting and optimizing natural convection in various applications. Let's move to Newton's law of cooling to quantify this process. Newton's law of cooling governs natural convection heat transfer. It states that heat transfer Q is given by Q is equal to H multiplied by A multiplied by Ts minus T infinity, where H is convective heat transfer coefficient in watts per meter square Kelvin. A is the surface area in meter square. Ts is the surface temperature, and T infinity is the ambient fluid temperature, both in Kelvin. The coefficient, that is the heat transfer coefficient H, is very crucial as it reflects the efficiency of heat transfer and depends on fluid properties, flow patterns, and surface orientation. In natural convection, H is typically lower as compared to forced convection due to slower fluid motion ranging from 2 to 20 watts per meter square Kelvin for gases and 5 to 1000 watts per meter square Kelvin for liquids. For example, a hot vertical wall transfers heat to the surrounding air with Q proportional to temperature difference. This law allows engineers to calculate heat transfer in the systems like radiator or electronic enclosures. By understanding H and its dependence on natural convection conditions, we can design systems that optimize passive heat transfer. Next, we will explore the dimensionless numbers that characterize the natural convections. Dimensionless numbers are essential for analyzing natural convections. The Grashof number represents the ratio of buoyancy to viscous forces driving fluid motion due to density differences. It depends on the thermal expansion coefficient, temperature difference, characteristic length, and kinematic viscosity. A higher Grashof number indicates stronger convection current. The Prandtl number PR is the ratio of momentum diffusivity to thermal diffusivity, indicating the relative thickness of velocity and thermal boundary layers. The Rayleigh's number is the product of Grashof's number and Prandtl number, which determines how the flow regime, that is laminar or turbulent. For a low Rayleigh number, the flow is a laminar, and for a high Rayleigh number, it becomes a turbulent, which enhances heat transfer. These numbers allow engineers to predict convection behavior without complex calculations. For example, a heated room, a high Rayleigh's number suggests vigorous air circulations. By correlating Rayleigh's number with the heat transfer rates, we can design systems like passive cooling or the solar collectors. These dimensionless numbers simplify the analysis of natural convection across the various geometries and fluids. So let's apply them to the heat transfer over a vertical surface in the next slide. Heat transfer over vertical surface is a common scenario in natural convection, such as in radiators or building walls. The Nusselt number, which relates the convective to conductive heat transfer, is correlated with the Rayleigh's number, that is Ra. For a laminar flow, the Rayleigh's number is less than 10 raised to 9. Nusselt number is given by Nu is equal to 0.59 Ra raised to 1 by 4, indicating moderate heat transfer. For a turbulent flow, when the Rayleigh's number value is more than 10 raised to 9, the Nusselt number is given by 0.01 Ra raised to 1 by 3, reflecting the enhanced heat transfer due to stronger convection currents. These correlations allow engineers to calculate the convective heat transfer coefficient H and predict the heat transfer rate using the Newton's law of cooling. For example, a vertical radiator transfers heat to room air with flow regime depending on Rayleigh's number. These formulas are used in the cooling walls, chimney design, and electronic enclosures. Vertical surfaces are ideal for natural convections because rising warm fluid creates strong circulations. Understanding this correlation helps to minimize passive heating or cooling, ensuring efficient thermal performance without mechanical input. Next, we will explore the natural convection over a horizontal surface. Natural convections over horizontal surfaces varies depending on the surface orientation. For a heated plate facing upwards, like a hot ceiling panel, strong convection currents forms a warm fluid rises freely, creating a vigorous circulation and efficient heat transfer. For a heated plate facing downwards, such as a floor heater. The convection is weaker because the warm, less dense fluid is trapped between the hot plate, reducing the circulation due to stability. The Nusselt number correlations for horizontal surface depends on Rayleigh number and its orientation. Sorry, for a heated plate facing downwards, such as a floor heater, the convection is weaker because the warm, less dense fluid is trapped between the plate, reducing the circulation due to stability. The Nusselt number correlation for the horizontal surface depends on Rayleigh number and its orientation, similar to vertical surfaces, but with different constants to account for the flow patterns. These principles are applied in sealing heating panels, solar collectors, and electronic devices where hot or the horizontal surfaces are common. For example, the solar collector uses upward facing convection to absorb heat efficiently. Understanding how orientation affects convection, it helps the engineers to design the systems that maximize the heat transfer to a specific configurations. By leveraging these differences, we can optimize passive thermal management in the buildings or the devices. So let's look at the natural convections in the enclosures in the next slide. Natural convections in enclosures occurs in the confined spaces, such as ovens, electronic casings, or double gaze windows. Heat transfer depends on the enclosure aspect ratio, that is, height to width and the Rayleigh's number Ra, which determines the flow regime. For example, in a vertical enclosures with one hot wall and one cold wall, fluid circulates as warm fluid rises along the hot side and the cool fluid sinks along the cold side. In the bottom heated enclosures, like oven, strong convection current forms, while the top heated setups have weaker circulation due to stability stratifications. These principles are used in the thermal insulations where low convections in the enclosed spaces reduces heat loss and in passive cooling systems for electronics where enclosures dissipate heat without fans. The Nusselt number for the enclosures is correlated with the Rayleigh number and aspect ratio guiding design. Understanding convections in the enclosures helps the engineers to optimize thermal performance in the confined systems, ensuring efficiency and reliability. Next, we will explore the practical applications of the natural convections. So natural convection has a diverse applications in engineering and nature. In heating systems, radiators use natural convection to warm rooms as hot air rises and circulates, providing energy efficient heating. Passive cooling in buildings leverages natural convection through ventilations or the chimney effects, reduces reliance on the mechanical systems and lowering energy cost. Cooling of electronic devices like the computers or the LEDs often relies on the natural convection through the heat sinks or the enclosures to dissipate the heat without fans, enhancing reliability. In nature, natural convection drives ocean currents and atmospheric circulations, influencing the climate and weather patterns. For example, warm ocean water rises, creating currents that distributes the heat globally. These applications highlight the simplicity and effectiveness of natural convection in managing thermal energy. By harnessing density-driven fluid motion, engineers and scientists create sustainable solutions for heating, cooling, and environmental systems. Understanding this application inspires innovative designs that balance performance and energy efficiency. So let's conclude with a summary of the natural convections. Now, to get the summary of the today's session, we have seen natural convection is a vital heat transfer mechanism driven by density difference due to temperature variations requiring no external forces. It is governed by Newton's law of the cooling, which is uh, focusing on the fluid circulations due to buoyancy effects. The key dimensional numbers, Kirchhoff's number, Prandtl number, and the Rayleigh number characterize fluid flow and heat transfer with the correlations of Nusselt numbers for laminar vertical surfaces. We have explored the convection over the vertical and horizontal surfaces in enclosures and its applications in radiators, passive cooling, electronics, and natural phenomena like ocean currents. Natural convection is widely used in heating, cooling, and industrial systems for their energy efficiency and simplicity. These processes enable sustainable designs that minimize the energy use while maintaining performance. I hope this lecture has deepened your understanding of natural convection and its impact. For the next time, consider how natural convection applies to a system you encounter like a radiator or a solar heater. Thank you, and let's continue to explore the science of heat transfer.